We are in 2.6 today, which is on rational functions. We have worked with rational functions before, but we have not really graphed them. And so we're going to look at more detail of their graphs and some characteristics of their graphs. Okay, so first of all, a rational function is a quotient of two polynomials. So I wrote it as r of x equals n of x over d of x, where n, I've just called it n of x because that's the numerator, d for denominator. And of course, the domain restriction on this is that d of x can't be 0. So we're going to look at the most basic rational function that we can, like, this is kind of like the parent function that we, like with x squared, this is 1 over x. So this is the simplest one that we have. Now, when we look at this, hopefully, it immediately springs to our mind that we should not use x equals 0 because that is our domain restriction, because that would cause division by 0. So we wonder, what happens when we get close to x equals 0? And so what we're going to do is we're going to plug in some values in both directions, right? So here's my 0, and basically I'm going to plug in some values here that are slightly smaller to the left of 0 and slightly bigger to the right of 0, okay? So we're going to plug them in here. So when I plug in 0, I get undefined, so that's this place in the middle. So let's start with the positive side. If I plug in a half into f, so let's just, I'll write this here. So f of a half is 1 over 1/2, right? So we multiply by the reciprocal, and this ends up being 2, okay? So then by the same argument, all of these, when I put in 1 over 1/10, I'm going to get 10. When I put in 1 over 100, I'm going to get 100. And when I put in 1 over 1,000, I'm going to get out 1,000, okay? Because we just multiply by the reciprocal each time. And so my numbers are getting really, really large, really big as I approach 0. So we say as x approaches 0 from the right, so that means from the positive side right? So 0 from this side is the way that we use this little plus sign. When we approach 0 from the right is how it's said. Then f of x, y, right? These are by y values. They're getting really large. We call that infinity. So f of x approaches infinity. All right, so let's look from the other side. Now, when I plug in, here's my f of a half. If I plugged in negative a half, then I would get out negative 2. And so by that same argument, I'm going to get out negative 10, negative 100, and negative 1,000. And so now, as my x is approaching 0, this time from the left is what we say. So this little sign says from the left, and the plus sign says from the right. From the right of whatever number is here, okay? So right means slightly bigger than the number, left means slightly smaller than the number. All right, so then as we approach 0 from the left this time, my numbers are getting really big again, except for they're negative. So we say that f of x approaches negative infinity, okay? So let's look at the graph. I got my Desmos out here. This is the graph of 1 over x. Okay, so let's look at our table here. So the way that this presents itself, right, I found out that as x approaches 0 from the right, so that means if I'm looking here, I'm looking from this direction, then f of x goes to infinity. See how it's shooting upward, okay? That's what happens there, because my graph is never going to touch the y-axis because x can't be 0 because it's part of my domain restriction. And then as I approach 0 from the left, right, I'm approaching this side, and my graph shoots straight down. So that approaches negative infinity. When this type of behavior happens at where the domain restriction is, we call this a vertical asymptote. So we're going to say that x equals 0 is a vertical asymptote. It's a line that's there. It's not really there, but it's a boundary line that my graph is never ever going to touch because I cannot divide by 0. So as long as I scoot all the way down there, it should never cross over this line here. All right. Now, while we're looking at it, we also have another type of asymptotic behavior here, is what we call it, where both of my graphs seem to sort of taper off here. In fact, neither one of these are going to cross over the x-axis either. We call these a horizontal asymptotes because see how they come out here and essentially they just level off. And it comes back out here and it also levels off, but from underneath. But they're still approaching 0 y values in both cases. So we say in this case that y equals 0, right? That's the x-axis, is the y equals 0, is a horizontal asymptote. Right? These behave really differently from polynomial functions, right? My polynomial functions don't have vertical asymptotes because there's no domain restrictions on them. And they don't have horizontal asymptotes either. So this is kind of a new thing, so we want to investigate how do we find them, because these graphs are really much more interesting than polynomial graphs that are just all smooth, right? So let's look at how we find vertical asymptote, or let's just talk about our asymptotes first, okay? So we're going to find both the vertical and the horizontal asymptotes. So this is how we go about it algebraically. We could look at the graph too and be able to see some of these, but this is how we show it algebraically. So the vertical asymptotes are the easiest thing to find. So we're going to say that f is n over d, right? We're just talking about two polynomial functions that are divided. That's a rational function. And the key factor before finding the vertical asymptotes is to make sure that n and d don't have any common factors. Meaning if I factored both the numerator and the denominator, they don't have factors in common. So if n had x plus 1 in it and d had x plus 1, then that's not how we would have to simplify that first. Okay. So a vertical asymptote is pretty straightforward. Once I simplify or factor my numerator and my denominator, I simplify any common factors, and anything that's left in the denominator, where I set that equal to 0, my domain restriction, that's going to be a vertical asymptote. Okay. So for instance, let's just do an example of that. So let's say I have f of x is equal to 1 over x plus 1. Okay. So I am going to have a vertical asymptote. There's no factors in common right here. If I'm going to have a vertical asymptote at x plus 1 is equal to 0. It's the same as the domain restriction. X equals negative 1 will be my vertical asymptote, which I'm just going to have it. Okay. So if I had f and instead I had x plus 1 over x squared minus 1, so the denominator now can be simplified or factored. And so I'm going to rewrite this as x plus 1 over x plus 1 times x minus 1. Now I know that I still cannot, my domain restriction here would be x can't be plus or minus 1, right? Because when I set these both equal to 0, I'm going to get that I can't plug in 1 or negative 1 because that would make my denominator 0. But these are both not vertical asymptotes because these have a common factor, right? So I simplify this first and I end up with 1 over x minus 1. That means that x equals 1 is a vertical asymptote. Okay. So this other factor here, right, the one that's got simplified, I still can't plug it in. It's not part of my domain restriction, or it is part of my domain restriction, but it's not a vertical asymptote. It's what we call a hole in the graph. So basically, my graph will be going along right there, and all of a sudden it'll just have this little bloop in it. Okay, so that's the difference. If I can simplify my factors, then it's not a vertical asymptote. But once I've done that, anything left in the denominator, I set it equal to 0, and that is my vertical asymptote. So that's pretty straightforward. All right. So let's now, for finding horizontal asymptotes, that's a little bit more challenging. So we have to look at the degree of the numerator versus the degree of the denominator. So one thing I should say is that vertical asymptotes, I can have a lot, as many possible vertical asymptotes. There's not a limit on them. So any number of factors that don't simplify and set them equal to 0, and I can have that many vertical asymptotes. Horizontal asymptotes are, we can either have 0, 1, or 2. There's no more than that. And usually with rational functions, we only get typically 1. There are functions that can give us more than one horizontal asymptote, but they're not usually rational. They're usually a different type. But the way that we can find out if something has a horizontal asymptote, if it's a rational function, is we compare the degrees. Okay? So the first thing here I have is that when the degree of the numerator, n of x, is greater than the degree of the denominator, there is no horizontal asymptote. Okay, so an example of that would be if I have f of x equals x squared plus 1 over x minus 1. Okay, this is an example of having no horizontal asymptote. Horizontal asymptotes occur basically as part of, I could actually do the division here as the division, and so since this numerator is bigger than the denominator, this is really improper. This is not going to have an asymptote because the numerator is going to grow so much faster than the denominator. So this has no horizontal asymptotes. Okay? So the second thing, right, so when the numerator is bigger than the denominator, then we don't get any horizontal asymptotes. When we have the numerator being less than the denominator, this is the degree of the denominator, then we get the automatic horizontal asymptote of y equals 0. Now we're going to understand why these are true later when we get into limits a little deeper, but for right now we can use this as our guideline. So an example of that, where the numerator has a smaller denominator, I'm just going to flip over my, I'm just going to flip my function, right? I just did the reciprocal of this. So now I have the bigger power on the bottom. So this ends up giving me an automatic y equals 0. Whenever the degree of the bottom denominator has a larger degree than the degree of the numerator, I always get this y equals 0. The reason being is because this is division. So when I'm putting in bigger and bigger values of x, this numerator is growing, but this denominator is growing way faster. So I end up dividing by something bigger and bigger and bigger, and it's growing much faster than this because the degree is bigger. And so what ends up happening is it shrinks and ends up being y equals 0. That's actually what happened with our function f of x equals 1 over x, right? The degree of the denominator was bigger than the degree of the numerator, and so that's why we saw the graph just like level out like that at y equals 0. So that's what it would look like, right? All right, and then the last one that we can have, so we did the case where the numerator was larger and we got none. We did the opposite where the numerator was smaller and we got y equals 0. And then we have the last case that if the degree of the numerator and the denominator are the same, then there's a horizontal asymptote at y equals the ratio of the leading coefficients. Okay, so let me give you an example of that one. Okay, so we have f of x is equal to 3x squared plus 4x minus 6 all over x minus 4x squared. Okay, so the degree of the numerator is 2, and the degree of the denominator, I have them a little bit switched here, but it's still the highest exponent, is also 2. This is going to give us a horizontal asymptote. Lines that are horizontal always begin with y, so these are equations of lines, so they should be x equals, and like horizontal are y equals, and vertical are x equals. And so we get a horizontal asymptote at the ratio of the leading coefficients. So the leading coefficient here is 3. The leading coefficient down here goes with the x squared, is -4. So we get -3/4 as our horizontal asymptote. Okay, so let's do a couple of examples. We're just going to find some vertical and horizontal asymptotes here. We'll start up here. So let's look at f of x is equal to 3x squared over x squared minus x minus 12. And we want to basically name all of the asymptotes, whether they're vertical or horizontal. Right, so then the first thing that I want to do is when I see anything, I want to factor it. So I'm going to rewrite f of x. The numerator I can't really factor, so I'm going to leave it alone. So my favorite quadratic, which factors as x minus 4 times x plus 3. So from the numerator, the easiest thing to find first is the vertical asymptotes. Okay, so I've got it factored. I don't have any factors in common. That means that both of these places where they're 0, those are vertical asymptotes. So I get x equals 4 and x equals negative 3. Exactly the same as the domain restriction would be. Now my horizontal asymptote, okay, so what kind of case do I have? Well, if I come back to this one, I mean, I can see it here too, but this is the easier one. I have degree 2 over degree 2. So the degree of the numerator matches the degree of the denominator. That's a y equals the ratio of their coefficients, which is 3 over the implied 1 here. So I get y equals 3 as a horizontal asymptote. Okay, so let's do another one of those. So I have f of x this time is equal to 2x squared minus 3x minus 2 over 3x squared minus 10x plus 8. Okay, so I'm going to factor everything in sight basically right now. So this will be equal to, I know that I'm going to have a 2x and an x here. My signs will be opposite, so I need a 2 here to have minus 4 and a plus 1 to have the minus 3. Okay, this isn't a factoring lesson, so if you need to refresh on how to factor, you know where the lecture is. All right, so now I'm going to have a 3x here and an x here. I know my signs will match because I have the plus. And so let's see, what do I need here? I need a 4 here. No, that's not 4 and 2. How about 2 here and 4 here? Because then that will give me the 6, that will give me the 4, and there we go. Okay. So this time, I know that this is, just looking at this, I'm going to get x cannot be 4/3 and x cannot be 2 from my domain restriction. But before I can see my vertical asymptote, I need to do this essentially. So what I'm going to find here at x equals 2 is a hole. We'll look more deeply at those in a little while. And then these two are left, so that simplifies to this. So this graph here will look identical to this graph here, except for at x equals 2, where if I zoom right into it, I'll see that there's a little space in there that's undefined. So I'm going to get a vertical asymptote only at x equals 4/3. So that's my vertical asymptote. All right, my horizontal asymptote, again, I'm kind of boring here, but I've got an x squared over an x squared again. I want to make sure that I don't have a higher power lurking over here, but I don't. So I get a vertical or a horizontal asymptote at y equals 2/3 because it's the ratio of the matching coefficients or the degrees. All right. Let me just do one more. If I have f of x equals x plus 1 over x squared minus 4, okay, so my denominator I can factor to x plus 1 over x plus 2 times x minus 2. I don't have any factors in common, so that leaves me knowing that both of my spots here that make my denominator 0 will be also horizontal asymptotes. So I get x equals -2 and x equals 2 are my two vertical asymptotes. And then my horizontal asymptote this time, a little different. Degree 1 in the numerator, degree 2 in the denominator. When the denominator is more powerful than the numerator, we get the automatic y equals 0. All right, so next time we are going to talk more in detail about how to graph these.